Idiomatic Go, Mastering Design Patterns, Best Practices, and Avoiding Anti-Patterns. Chapter 1, Welcome to the Go Way. 1.1 Introduction. Why Go? In today's fast-paced digital world, software needs to be robust, performant, and scalable. From global web services handling millions of concurrent users to critical infrastructure components, the demands on modern applications are immense. For many, the Go programming language, often referred to as Golang, has emerged as a powerful and pragmatic solution to these challenges. Go was created at Google by Robert Griesemer, Rob Pike, and Ken Thompson, largely as a response to the complexities and compile times of larger software projects written in languages like C++ and Java. They sought a language that combined the performance of compiled languages with the productivity and ease of use found in dynamic languages. The result is a language designed with modern multi-core processors, network systems, and large codebases firmly in mind. You'll find Go powering a significant portion of today's cloud infrastructure, from the core of Docker and Kubernetes to countless backend services and command line tools. Its appeal lies in its rapid compilation, which translates to quicker development cycles, its built-in support for concurrent operations, which simplifies the creation of highly responsive systems, and its efficient garbage collection, contributing to dependable performance. In essence, Go strikes a compelling balance between developer productivity and raw execution speed. 1.2 The philosophy of Go. More than just a set of syntax rules, Go embodies a distinct philosophy that shapes how developers approach software design. Understanding this philosophy is key to writing effective and maintainable Go programs. Simplicity and minimalism. One of Go's most striking features is its commitment to simplicity. It has a comparatively small language specification with fewer keywords and a straightforward type system. The creators intentionally omitted many features common in other languages, such as class-based inheritance, generic types, until Go 1.18, and even then, its implementation aligns with Go's simplicity, exceptions, and complex type hierarchies. The goal here is to reduce cognitive load. With less syntactic sugar and fewer ways to achieve the same task, Go code tends to be more consistent and easier to read and understand, regardless of who wrote it. Think of Go as a well-designed hand tool, simple, focused, and incredibly effective for its intended purpose. It eschews complexity, preferring explicit and clear solutions. Composition over inheritance. Unlike many object-oriented languages that rely on class inheritance to build hierarchies of types, Go champions composition. Instead of a child class inheriting behavior from a parent, Go encourages you to build complex behaviors by combining smaller, single-purpose components. This is primarily achieved through Go's powerful interface system and struct embedding. This approach leads to dramatically reduced coupling between different parts of your code. Your types don't need to fit into a rigid, predefined hierarchy. Instead, they just need to provide specific behaviors as defined by an interface. This makes code more flexible, easier to test in isolation, and less prone to the fragile base class problem common in deep inheritance trees. Concurrency as a first-class citizen. The world is concurrent. Modern applications operate across multiple cores, handle many incoming requests simultaneously, and perform numerous tasks in parallel. Go was designed from the ground up to make concurrent programming simpler and safer. Its core primitives for concurrency are goroutines and channels. Goroutines are incredibly lightweight, independently executing functions that are managed efficiently by the Go runtime. You can easily launch thousands or even millions of them without burdening the operating system. Think of them as tiny, efficient workers. Channels, on the other hand, are typed conduits designed for communication. They provide a safe and synchronized way for goroutines to send and receive values. While goroutines are your workers, channels are the well-organized pipelines or conveyor belts that allow these workers to pass messages and coordinate their efforts. This approach significantly reduces the complexities and common pitfalls associated with traditional thread-and-lock-based concurrency models. Explicit error handling. In Go, errors are not hidden behind exceptions. They are an explicit part of a function's return signature. Functions that might fail typically return two values, the result and an error value. It is then the developer's responsibility to check this error. This explicit approach forces developers to consider potential failures at every step. It discourages silent failures and promotes the creation of more robust and predictable code. While it might seem verbose initially, it leads to a clear and consistent flow of error propagation, making it easier to understand exactly where and why something went wrong. Opinionated tooling. Go comes with a robust set of built-in tools that are part of its standard distribution. Tools like Go FMT automatically format your code to a single, consistent style, eliminating endless debates about tabs versus spaces or brace placement. GoVet provides static analysis, catching suspicious constructs and common programming mistakes early. GoTest offers a seamless way to write and run automated tests and benchmarks. This opinionated tooling encourages consistency across different projects and teams. It reduces the mental overhead of choosing and configuring tools, allowing developers to focus on writing code. The consistent structure and formatting make it much easier for any Go developer to jump into an unfamiliar codebase and immediately feel at home. 1.3. What is Idiomatic Go? Given Go's strong philosophy and opinionated design, aspiring Go developers quickly encounter the concept of idiomatic Go. Writing idiomatic Go means crafting code that feels natural and familiar to other Go developers. It's about adhering to the language's conventions, embracing its design principles, and leveraging its unique features effectively. It's not just about writing code that works, it's about writing code that is beautifully Go native. For instance, rather than trying to force object-oriented design patterns into Go using complex type hierarchies, an idiomatic approach would lean heavily on Go's interfaces for polymorphism. Similarly, for concurrent operations, preferring channels for communication between goroutines over shared memory protected by mutexes, though mutexes have their specific, valid uses, is often the more idiomatic Go solution. Following idiomatic practices has a profound impact. It makes your project instantly more readable to other Gophers, significantly reduces the learning curve for new team members, and ensures the code is easier to maintain and extend over its lifecycle. It cultivates a shared understanding and approach across the Go community. 1.4. How this book will guide you. This book is designed to be your comprehensive guide to mastering the Go way. We will move beyond the basic syntax to delve into the underlying design philosophy that makes Go so powerful. Our journey will cover several crucial areas. Design patterns. We will explore how classic design patterns apply, or often don't fully apply, within the Go ecosystem, and more importantly, how Go's unique features lead to its own set of distinct and powerful patterns. Best practices. You will learn established best practices for structuring Go applications, writing clean and maintainable code, effective testing, and utilizing Go's powerful concurrency features robustly. Anti-patterns. Just as important as knowing what to do is knowing what to avoid. We will identify common pitfalls and anti-patterns that can lead to fragile, unmaintainable, or inefficient Go code, showing you how to steer clear of them. Throughout these chapters, the focus will always be on practical application and, crucially, understanding the why behind the recommendations. By the end, you will not only be able to write working Go code, but you will also develop the intuition and skills to craft elegant, efficient, and truly idiomatic Go applications. Let's begin our journey. Chapter 2 goes building blocks beyond the basics. To truly master Go, it's essential to move beyond the basic syntax and delve into its fundamental building blocks. These are the constructs that shape Go's unique characteristics and enable its powerful designs. Understanding them deeply will pave the way for writing idiomatic, robust, and performant applications. 2.1 Interfaces. The heart of polymorphism in Go. In the world of programming, polymorphism refers to the ability for different types to be treated as a single type, allowing code to operate on a variety of data in a uniform way. In many languages, this is achieved through class hierarchies and explicit inheritance. Go takes a different, simpler, and arguably more flexible approach: interfaces. Go's interfaces are implicitly satisfied. This means that a type automatically satisfies an interface if it implements all the methods declared by that interface. There's no special keyword or declaration required, like implements or extends found in other languages. For example, if you define an interface called logger that specifies a method log that takes a string message, any struct or type that provides a public log method of that signature automatically qualifies as a logger. This implicit nature is often referred to as duck typing. If it walks like a duck and quacks like a duck, then it's a duck. Go cares about what a type does its behavior through methods, not what it is its class hierarchy. This leads to extremely loose coupling between components. A function expects an interface, and any type that fulfills that interface can be passed in, regardless of its original structure or where it came from. Go idioms often promote small interfaces, ideally with a single method or a few highly cohesive methods. Think of the standard library's IOReader or IOWriter interfaces, each with just one method, read or write respectively. This aligns well with the single responsibility principle, an interface defining one specific capability, facilitating greater composition and easier testing. A common pattern you'll encounter is the empty interface, denoted as interface, or any from Go 1.18 onwards. This interface technically specifies 0 methods, meaning every type satisfies it. While interface can hold any value, its overuse can lead to a loss of type safety, pushing type-related errors from compile time to runtime. It often necessitates verbose type assertions or type switches to discover and manipulate the underlying concrete type. For true generic programming, like building a generic list or map that works with any element type, Go 1.18 and later introduce generics, type parameters, which provide a type-safe and idiomatic alternative to the empty interface. 2.2 Concurrency primitives, goroutines, channels, and context. Concurrency is not just an add-on in Go, it's a fundamental aspect of its design. Go provides powerful, yet simple, primitives that make concurrent programming intuitive and efficient. Goroutines. At the heart of Go's concurrency model are goroutines. These are lightweight, independently executing functions. You simply prepend the Go keyword before a function call to execute it as a goroutine. What makes them powerful is that they are managed by the Go runtime, not directly by the operating system. Thousands, or even millions, of goroutines can be multiplexed onto a smaller number of OS threads, making them far cheaper to create and manage than traditional threads. Think of goroutines as tiny, efficient, and numerous workers, each capable of performing a task concurrently. Channels. While goroutines perform work, channels enable communication and synchronization between them. Channels are typed conduits through which you can send and receive values. They are designed to be safe, ensuring that data passed through them is free from race conditions. You can have unbuffered channels, which require both a sender and a receiver to be ready simultaneously, making them useful for strict synchronization, or buffered channels, which can hold a certain number of values before blocking. Channels provide a clear and explicit way for goroutines to coordinate. Imagine them as a well-organized pipeline or conveyor belt for passing messages and data between your workers, ensuring tasks are handed off smoothly and predictably. Go's select statement is also crucial when working with multiple channels. It allows a goroutine to wait on multiple communication operations, sends or receives, and proceed with the one that's ready first, enabling non-blocking communication and sophisticated control flow. Context. As applications grow, especially networked services, managing the lifecycle of goroutines becomes critical. This is where the context package, a truly indispensable part of Go's concurrency toolkit, comes into play. A context object propagates important signals and values down a call chain, across API boundaries, and between goroutines. Its primary uses are cancellation, signaling to goroutines that their work is no longer needed, e.g., a client disconnected, an HTTP request timed out. Long-running operations within goroutines can monitor the done channel of the context and exit gracefully when it closes. Timeouts and deadlines, similar to cancellation, but with a built-in time limit for an operation to complete. Value propagation, carrying request scope data, like authentication tokens, trace IDs, or user IDs, throughout a chain of operations without polluting function signatures with numerous arguments. Pass the context, as the very first argument to functions that might perform I/O or other long operations that could benefit from cancellation or timeouts. It acts like a lifespan manager or a request passport that travels with an operation, ensuring cohesive behavior across your system. The sync package. While channels are the preferred method for communication and coordination, the sync package provides essential lower-level synchronization primitives for specific scenarios, especially when protecting shared memory. Sync mutex, a mutual exclusion lock used to protect shared data from concurrent access. Only one goroutine can hold the lock at a time, ensuring that critical sections of code are executed serially. SyncRW mutex provides a reader-writer lock, allowing multiple readers but only one writer. SyncWait group, used to wait for a collection of goroutines to complete. A wait group counts the number of active goroutines. You add to the counter before launching a goroutine, call done when it finishes, and wait blocks until the counter reaches 0. Sync, once, guarantees that a specific function, typically an initialization function, runs exactly once, even if called concurrently by multiple goroutines. This is invaluable for lazy, thread-safe initializations. 2.3 Error handling, the Go way. Go famously or infamously, depending on who you ask, handles errors explicitly. There are no exceptions to catch elsewhere. Instead, functions return the error type as their last return value. The convention is to check it immediately. If err equals nil/handle error. This pattern, while pervasive, forces developers to acknowledge and deal with potential failures directly, leading to more resilient code by design. Go 1.13 significantly enhanced error handling with error wrapping. By using fmterrorf with the %w verb, you can wrap an original error with additional textual context. This creates a chain of errors, preserving the deeper cause while providing call stack relevant information. This is crucial for debugging, as you can see not just what went wrong, but where it went wrong and why it initially failed. To intelligently inspect these wrapped errors, Go provides functions in the errors package. Errors is err targeter. This function checks if an error is or wraps a specific target error value anywhere in its chain. This is perfect for checking against sentinel errors, predefined error variables like IOEOF or OSER not exist. Errors as err and target var. This checks if an error is or wraps a specific type of error. If it does, it unwraps the error and assigns it to target var, which must be a pointer to an error type. This allows you to retrieve structured error information from custom error types you've created. While explicit error returns are the norm, Go does have panic and recover. A panic immediately stops normal execution. It's intended for truly unrecoverable programming errors, such as dereferencing a nil pointer or an out-of-bounds array access situations that indicate a bug that cannot be gracefully handled. Recover can catch a panic within a defer function, but it's rarely used for general control flow. Think of panic as an emergency brake. It should be used very sparingly and only when the program cannot proceed safely. For most conditional failures, return an error. 2.4 Modules and package management. Effective dependency management is crucial for any modern programming language, and Go addresses this through Go modules, introduced in Go 1.11 and becoming the default in Go 1.14. A Go module is a collection of related Go packages that are versioned together. Every Go project is typically managed as a module. A module is defined by a Go mod file in its root directory. This file declares the module's path and lists all its direct and indirect dependencies, along with their semantic versions, e.g., github.com/gin-gonic/gin v1.7.2. Alongside Go mod, you'll find a Go sum file. This file contains cryptographic checksums of the module dependencies, ensuring that the fetched dependencies are exactly what's expected and haven't been tampered with. This provides a strong integrity check for your project's build. Key commands for managing modules include go mod init module path, initializes a new module in the current directory. Go get module path, adds a new dependency or updates an existing one to its latest compatible version. Go mod tidy, adds any missing module requirements and removes unused ones, cleaning up the Go mod and Go sum files. Beyond external dependencies, package organization within your own module is critical. Go encourages organizing code into small, focused packages, each with a clear, single responsibility. This promotes modularity and makes your code base easier to navigate and test. A common convention is the internal directory. Any package placed directly within an internal directory, e.g., yourmodule/internal/mypackage, cannot be imported by code outside of your module. This strict enforcement by the Go compiler is a powerful way to encapsulate implementation details and ensure architectural boundaries, making certain parts of your code private to your module while still being structured as separate packages. By understanding and leveraging these core building blocks interfaces, the concurrency primitives, robust error handling, and robust module management, you lay a solid foundation for writing high-quality Go applications. These are the tools that will empower you to apply design patterns, adhere to best practices, and avoid the common pitfalls we will discuss in later chapters. Chapter 3. The Go approach to design patterns. In the journey of becoming a proficient Go developer, it's not enough to simply understand the language's syntax and core features. To build maintainable, scalable, and robust applications, you need to understand how to structure your code effectively. This is where the concept of design patterns becomes crucial. 3.1. What are design patterns? At their core, design patterns are well-established, reusable solutions to common problems encountered during software design and development. They represent best practices that experienced software engineers have discovered and refined over many years. Think of them as high-level blueprints or recipes for solving recurring architectural challenges, rather than concrete implementations you copy wholesale. Design patterns provide a shared vocabulary among developers, making it easier to discuss and understand complex software designs. When a developer says, "We'll use a factory pattern here," others skilled in design patterns immediately grasp the general structure and intent without needing a detailed explanation of every line of code. Importantly, design patterns are typically language-agnostic concepts. For example, the idea of separating object creation from its usage, a creational pattern, can be applied in almost any programming language, but its specific implementation will differ based on the language's features and idioms. This distinction is particularly relevant when discussing Go. 3.2 Go's perspective on patterns. Go's unique philosophy and design choices mean that its approach to design patterns differs significantly from languages rooted in classical object-oriented programming, like Java or C++. Many of the Gang of Four, GoF patterns, which originated from the C++ and Smalltalk worlds, were designed to solve problems arising from complex class hierarchies and inheritance. Since Go strongly favors composition over inheritance and has a very explicit type system, many of these GoF patterns need significant adaptation, or in some cases, are rendered entirely unnecessary because Go provides simpler, more direct built-in ways to achieve the same goals. Here are some key aspects of Go's perspective. Simplicity leads to simpler solutions. Go's emphasis on simplicity often means that problems solved by intricate patterns in other languages can be handled directly with straightforward Go code. The preference is for explicit, readable code over abstract, layered patterns that might obscure the actual logic. Often, less code is better code. Interfaces are powerhouses. Go's implicit interfaces are incredibly powerful and fundamental to its design patterns. They allow for flexible and decoupled designs without the need for complex abstract factories or bridges. Many problems addressed by patterns like bridge or strategy in traditional OOP can be cleanly solved in Go using small, focused interfaces. First-class functions. Go treats functions as first-class citizens, meaning they can be assigned to variables, passed as arguments, and returned from other functions. This capability simplifies the implementation of patterns like strategy, command, or decorator, often allowing them to be expressed as simple function wrappers or closures rather than requiring dedicated object structures. Concurrency primitives change the game. Go's built-in goroutines and channels are so fundamental and powerful that they form the basis of an entirely separate category of concurrency patterns. These patterns are unique to Go and enable highly scalable and robust concurrent systems. Consider the singleton pattern, which ensures only one instance of a class exists. In a traditional OOP language, this might involve private constructors and static methods. In Go, it's typically handled more directly using sync. Once, a standard library primitive guaranteeing a function executes only once, combined with a package-level variable. Similarly, the decorator pattern, which wraps objects to add behavior, is often achieved in Go via simple function composition using closures rather than class hierarchies. The key takeaway is that when approaching design patterns in Go, you should always ask, is there a simpler, more idiomatic Go way to solve this? The answer is often yes. 3.3 Categorization of patterns in Go. To better organize our discussion, design patterns are commonly grouped based on their purpose. This book will follow a categorization that thoughtfully blends traditional pattern classifications with Go's unique features, particularly its strengths in concurrency. Creational patterns. These patterns are concerned with how objects are created. They aim to abstract the instantiation process, making the system independent of how its objects are created, composed, and represented. This provides flexibility in choosing appropriate object creation techniques. Structural patterns. These patterns deal with how objects and classes are composed to form larger structures. They focus on how to build relationships between entities, promoting efficient communication and organization while maintaining flexibility and efficiency. Behavioral patterns. These patterns are concerned with algorithms and the assignment of responsibilities between objects. They describe how objects communicate and interact, ensuring that operations are performed gracefully and responsibilities are well distributed. Concurrency patterns. This is a particularly vital category for Go, leveraging its built-in coroutines, channels, and other synchronization primitives. These patterns specifically address challenges related to parallel execution, communication, and synchronization in multi-threaded or distributed environments, enabling the creation of scalable and resilient systems. In the following chapters, we will explore specific patterns within each of these categories, explaining their purpose, how they are typically implemented in idiomatic Go, and when to apply them, or, just as importantly, when a simpler Go approach might be preferred. Chapter 4. Creational patterns in Go. Creational patterns are design patterns that deal with object creation mechanisms. They aim to abstract the instantiation process, making the system independent of how its objects are created, composed, and represented. By controlling how objects are created, these patterns provide flexibility, reduce complexity, and help manage object life cycles effectively. In Go, with its distinct approach to types and composition, these patterns often manifest in simpler, more direct ways compared to traditional object-oriented languages. 4.1 Simple Factory. The simple factory is not a formal gang of four pattern, but it's a widely used and highly intuitive creational pattern that serves as a foundational concept. Purpose. The simple factory's core purpose is to create objects without exposing the exact instantiation logic to the client. It centralizes object creation for a family of related types, allowing the client code to depend on an interface rather than a concrete implementation. This means if you decide to change the internal implementation of a specific object, the client code that uses the factory doesn't need to be modified. Go implementation. In Go, a simple factory is typically implemented as a single function that takes parameters describing the type of object to create. This function then uses conditional logic, like a switch statement, to instantiate the correct concrete type and returns it as an interface. Conceptual example. Imagine building a graphics application where you need to create various shape objects like circles, squares, or triangles. All these shapes might implement a common shape interface with methods like area or draw. Instead of the client code directly calling new circle or new square, you would provide a factory function, say new shape, shape type string, shape error. The new shape function would receive a string like circle or square, internally decide which concrete shape to create, and return the shape interface. If an unknown shape type is provided, it would return nil and an error. Benefit. This pattern decouples the client code from the specific concrete implementations of the objects it uses. This makes the system more flexible and easier to maintain. If you later introduce a new type of shape, say a pentagon, you only need to modify the new shape factory function, not every piece of client code that requests shapes. 4.2 Builder pattern. When an object has a large number of parameters, especially if many of them are optional, constructing it can become cumbersome. This is where the builder pattern shines. Purpose. The builder pattern helps construct complex objects step by step. It separates the construction of a complex object from its representation, allowing the same construction process to create different representations. It prevents the creation of telescoping constructors with many overloaded parameters, which are hard to read and maintain. Go implementation. In Go, the builder pattern typically involves creating a separate builder struct. This builder struct holds all the parameters needed to construct the final object. Methods are defined on the builder that allow you to set these parameters. These methods usually return a pointer to the builder itself, enabling method chaining, e.g., builder with name, Alice, with age, 30, build. Finally, a build method is called on the builder, which validates the parameters and returns the fully constructed object, often an immutable one or an error if validation fails. Conceptual example. Consider creating a report object that can have various sections like a header, financial data, executive summary, and different formatting options. Instead of a single new report function with dozens of arguments, you might have a report builder. You would start by creating the builder. Builder equals new report builder. Then you chain methods to set the desired properties. Builder add header, quarterly metrics, add financials data, set page orientation, landscape. Finally, you build the report. Report equals builder build. The build method could then validate that all required sections are present before creating the final report. Benefit. The builder pattern leads to much clearer and more readable object construction code, especially for objects with many optional parameters. It allows for validation at different stages, preventing illegal states during construction, and gracefully handling invalid parameter combinations by returning an error. It also supports creating immutable objects, as all properties are set before the object is fully assembled. 4.3 Singleton, the Go way. The singleton pattern ensures that a type has only one instance and provides a global point of access to that instance. While a powerful concept, it is often considered an anti-pattern in modern software design due to its potential downsides regarding testability and hidden dependencies. However, there are scenarios where a single instance of a resource, like a global configuration manager or a single instance of a logger, is genuinely appropriate. Purpose. To guarantee that a class has only one instance and provides a single, well-known access point to it. Go implementation. The most common, thread-safe, and idiomatic way to implement a singleton in Go is by leveraging the sync, once primitive from the standard library. Sync once guarantees that a function, typically the one that creates the singleton instance, will be executed exactly once, even if called concurrently by multiple goroutines. The singleton instance itself is usually stored in a package-level variable. Conceptual example. Suppose you need a single, global database connection pool for your application to manage connections to a database. You would define your database connection pool type and often have a package-level variable for the instance, var global db pool database connection pool. Then, you'd create a function to get this instance, typically getDBPool, database connection pool. Inside getDBPool, you would use sync once like this, var once sync once. Once do func. This function will only be executed once, even with concurrent calls. Global dbPool equals initialize database pool, your actual initialization logic. Return global dbPool. Subsequent calls to get dbPool would just return the already initialized global db pool. Caution: as mentioned, the singleton pattern introduces global mutable state, which can make testing harder, create hidden dependencies, known as tight coupling, and complicate concurrency by making it harder to track modifications to the single instance. In Go, explicit dependency injection, where you pass dependencies between components, is generally preferred. Use sync once for true single-shot initializations, but carefully consider if a global singleton instance is truly the best architectural choice for your problem, especially when that instance is responsible for managing a shared and mutable resource. 4.4 Functional Options Pattern Go-Specific Alternative. The functional options pattern isn't a traditional object-oriented pattern, but is a highly idiomatic Go pattern that effectively solves the problem of flexible and extensible object configuration, often as a cleaner alternative to the builder pattern or constructors with many optional parameters. Purpose: to provide a flexible and extensible way to configure objects or functions using variadic arguments that are functions themselves. It allows for a clean, readable API for setting optional parameters, especially in constructor functions. Go implementation. In this pattern, the constructor function for an object takes a variadic list of option functions. Each option function is a closure that encapsulates a specific configuration step and typically modifies the object being constructed or a configuration struct. The option functions usually have a signature like func t, where t is the type being configured. Conceptual example: consider a server type that can be configured with various settings. A specific port, a custom logger, a read timeout, or a maximum number of concurrent connections. You'd define an option type, usually mimicking a function signature, type server option func server. Then you define individual option functions, for example, func with port, port int server option, return func s server, sport equals port, func with logger, logger my logger, server option, return func s server, slogger logger. And your new server constructor would look like this: func new server, iter string options, server options server. Inside new server, after initializing a default server instance, you would loop through the options slice and apply each function. For opt equals range options, opt srv, apply the option to the server instance. A client then creates a server like this: srv equals new server, 8080 with port 8081 with logger my custom logger. Benefit: this pattern is incredibly flexible and extensible. You can add new configuration options without modifying the existing constructor function's signature or affecting existing client code. It's highly readable, as the options clearly state their intent, and well-suited for Go due to its support for first-class functions and closures. It offers a powerful and elegant way to manage complex configurations that is often cleaner and more maintainable than a full-blown builder for simple configuration tasks or a constructor with an ever-growing list of parameters. It is a prime example of a Go-specific solution to a common software problem. Chapter 5: Structural Patterns in Go. Structural patterns are concerned with how objects and classes are composed to form larger structures. They focus on establishing relationships between entities, promoting efficient communication and organization while maintaining flexibility. In Go, with its emphasis on composition through interfaces and first-class functions, many of these patterns find elegant and often simpler implementations than in traditional object-oriented languages. 5.1 Adapter Pattern. Sometimes you encounter a situation where an existing component provides useful functionality, but its interface doesn't match the interface your client code expects. Trying to force a direct connection would either require modifying the existing component, which might be impossible if it's third-party or legacy code, or rewriting your client code. This is where the adapter pattern comes to the rescue. Purpose: the adapter pattern allows objects with incompatible interfaces to collaborate. It acts as a wrapper or a middleman that translates the interface of one type, the adaptee, into another interface that a client expects, the target. It bridges the gap between two otherwise incompatible interfaces. Go implementation. In Go, the adapter pattern is straightforward due to its implicit interface satisfaction. You typically create a new struct that embeds or holds a reference to the type you're adapting, the adaptee. This new struct then implements the desired target interface by translating method calls from the target interface into calls appropriate for the adaptee. Conceptual example: imagine you have a legacy logging system with a specific legacy log, message string, function, but your modern application expects a logger interface with a write, level string, message string method. You can create a legacy logger adapter struct. This adapter would embed or contain the legacy logger. It would then implement the logger interface's write method. Inside write, it would translate the level and message to be compatible with legacy log, perhaps ignoring the level or mapping it to a prefix for the message before calling legacy log. This allows your application to use the legacy logger adapter as if it were a standard logger, without ever knowing the details of the legacy system. The original legacy log function remains untouched. Benefit: the adapter pattern enables the reuse of existing components that otherwise couldn't work together due to interface mismatches. It facilitates easier integration with new or legacy systems, promoting interoperation and reducing the need for costly rewrites. 5.2 Decorator Pattern. The decorator pattern provides a flexible alternative to subclassing for extending functionality. Instead of creating a new subclass for every combination of behaviors, you wrap an object with other objects that add new responsibilities. Purpose: to dynamically add new behaviors or responsibilities to an object without modifying its structure. It attaches responsibilities to objects at runtime, offering a flexible alternative to traditional inheritance for extending functionality. Go implementation. Go's strong support for interfaces and first-class functions makes the decorator pattern particularly elegant. One common approach involves creating a new struct that embeds the interface of the object being decorated, or the concrete type if you're not using an interface. This decorator struct also implements the same interface. The decorator's methods then perform additional logic, e.g., logging, metrics, authentication, validation, either before or after delegating the call to the embedded decorated object. Another idiomatic Go approach, especially for function-based operations like HTTP handlers or middleware, is to use function wrappers or higher-order functions. Here, a function returns another function that wraps the original. Conceptual example: consider an HTTP handler interface that defines how to handle incoming web requests. You might have a basic MyCore handler that performs the primary request processing. Now, you want to add logging for all requests, measure request latency, and ensure authentication for certain paths. Instead of modifying MyCore handler or creating many subclasses, e.g., logged authenticated latency measured handler, you'd create logging handler, metrics handler, and auth handler decorators. Each decorator would take an HTTP handler as input, do its specific work, and then pass the request along to the next handler. A request might flow like this: auth handler wraps metrics handler, which wraps logging handler, which finally wraps MyCore handler. Each layer adds its behavior without MyCore handler needing to know about it. In function-based decorators, this often looks like auth middleware, metrics middleware, logging middleware, MyCore handler. Benefit: the decorator pattern offers extremely flexible functionality extension. You can combine multiple decorators in various ways, allowing for dynamic additions of features. It avoids the exponential growth of subclasses that would be required with traditional inheritance and keeps the core components clean and focused on their primary responsibilities. Think of it like adding layers to cake. Each layer adds new flavor or texture without permanently changing the fundamental cake. 5.3 Facade Pattern. As software systems grow, they often become a collection of many interconnected classes and subsystems. Clients interacting with such a system typically need to coordinate calls across several of these components to perform even a simple task. This can lead to complex client code that is highly coupled to the internal workings of the subsystem. Purpose: the facade pattern provides a simplified, high-level interface to a complex subsystem. It hides the underlying complexity of multiple, interacting interfaces or components behind a single, unified entry point. This makes the subsystem easier to use and reduces the dependency between the client and the numerous internal components. Go implementation. A facade in Go is typically implemented as a new struct or a set of functions that encapsulates the underlying subsystem components. The facade's methods then orchestrate calls to these internal mechanisms, presenting a much simpler and more cohesive API to the client code. The facade doesn't add new functionality, but simplifies an existing interface. Conceptual example: Imagine an e-commerce order processing system. Placing an order might involve checking inventory, processing payment, sending order confirmations, and updating customer records. Each of these could be handled by separate, complex services: inventory service, payment service, notification service, customer service. A order facade, e.g., an order service struct, could expose a single method: place order item, quantity, payment info, customer ID, error. Internally, this facade would coordinate all the necessary calls to inventory service checkstock, payment service process payment, notification service send confirmation, and customer service update history. Benefit: the facade pattern simplifies client codes interaction with a complex system, reducing dependencies and making the system easier to understand and use. It also helps structure a large application into layers, providing a clear separation of concerns. It's like having a universal remote control for a home theater system. It gives you one simple interface to control many complex devices. 5.4 Proxy Pattern. The proxy pattern provides a surrogate or placeholder for another object to control access to it. It introduces an intermediary that stands in for the real object, performing additional actions before or instead of forwarding a request to the actual object. Purpose: to control access to an object, add extra functionality, or delay resource-intensive operations until they are truly needed. The proxy acts as an intermediary, intercepting calls to the real object's methods. Go implementation. A proxy struct holds a reference to the actual object, the real subject, and implements the same interface as the real subject. It intercepts calls to the real object's methods. Inside these intercepted methods, the proxy can perform pre-processing, e.g., security checks, logging, caching, delegate the call to the real subject, and then perform post-processing. Conceptual example: consider a scenario where you're accessing a large dataset, perhaps from a remote database or an expensive external API. Accessing small pieces of this data repeatedly might be slow. You could introduce a data service proxy that implements the same data service interface as your actual remote data service. When a client requests data, the data service proxy first checks its internal cache. If the data is available in the cache, it returns it immediately without ever contacting the remote data service. If not, it fetches the data from remote data service, stores it in the cache, and then returns it. Other types of proxies include protection proxy, controls access based on user permissions or roles. Remote proxy manages communication with an object located in a different address space, e.g., across a network. Virtual proxy creates resource-intensive objects on demand, lazy loading. Benefit: the proxy pattern provides controlled access to an object. It can improve performance through mechanisms like caching, enforce security policies, manage resource lifecycle, lazy loading, and introduce aspects like logging or monitoring without modifying the core logic of the real object. It offers a structured way to add value around an existing object's functionality. Chapter 6: Behavioral Patterns in Go. Behavioral patterns are concerned with algorithms and the assignment of responsibilities between objects. They describe how objects communicate and interact, ensuring that operations are performed gracefully and responsibilities are well distributed. These patterns often focus on the flow of control and data between objects, providing solutions for common interaction paradigms. In Go, with its flexible interfaces and first-class functions, many behavioral patterns can be implemented elegantly and concisely. 6.1 Strategy Pattern. Imagine you have a single problem that can be solved in several different ways, and you want to be able to pick which solution to use at runtime. Rather than embedding all the possible solutions in one large, conditional block, the strategy pattern allows you to encapsulate each algorithm separately. Purpose: the strategy pattern defines a family of algorithms, encapsulates each one, and makes them interchangeable. This allows an algorithm to be selected dynamically at runtime, decoupling the algorithm from the client that uses it. The client effectively delegates the choice of algorithm to an external strategy object. Go implementation. In Go, the strategy pattern is typically implemented by defining an interface for the strategy, the algorithm. Each concrete strategy type then implements this interface. The client often called the context, holds a reference to an object that satisfies this strategy interface, and then delegates the execution of the algorithm to that strategy object. Go's ability to treat functions as first-class citizens also allows using functions directly as strategies, sometimes simplifying an implementation further. Conceptual example. Consider an e-commerce application that needs to calculate shipping costs. The cost calculation might depend on the destination, weight, and chosen shipping carrier, e.g., standard, express, international. Instead of a large switch statement in the shipping calculator, you can define a shipping strategy interface with a method like calculate cost, order, float 64. You could then have concrete strategies such as standard shipping strategy, express shipping strategy, and international shipping strategy, each implementing calculate cost differently. The shipping calculator struct would hold a shipping strategy interface. At runtime, you would set the appropriate strategy, e.g., based on user selection or order destination, and then simply call calculator.strategy.calculateCost.order. Benefit: the strategy pattern leads to cleaner code by eliminating large conditional blocks, improves extensibility, new strategies can be added without modifying existing client code, and promotes reusability of algorithms. It makes code more flexible and easier to maintain. 6.2 Observer Pattern. In many applications, one object's state change needs to notify other dependent objects, without those dependents being tightly coupled to the changed object. This is the core problem the observer pattern solves. Purpose: to define a one-to-many dependency between objects so that when one object, the subject or publisher, changes its state, all its dependent objects, the observers or subscribers, are automatically notified and updated. This promotes loose coupling between the subject and its observers. Go implementation. While traditional implementations involve subject and observer interfaces, in concurrent Go, this pattern often leverages channels for asynchronous notification. A subject might have a slice of functions or channels to notify. Conceptual example: imagine a stock trading application. A stock market, the subject constantly updates its stock prices. Multiple trading bots, observers, and display widgets, other observers, need to react to these price changes. The stock market would have methods to register and deregister observers. When a stock price changes, the stock market iterates through its registered observers and calls an update method on each of them, passing the new stock data. Alternatively, in a more Go idiomatic concurrent design, the stock market could publish price updates to a channel, and each trading bot or display widget could launch a Go routine that listens on this channel. This allows for asynchronous, decoupled event handling. Benefit: the observer pattern promotes loose coupling between the subject and its observers, allowing them to vary independently. It supports distributed event systems and makes components more reusable by decoupling their communication. 6.3 Command Pattern. Sometimes you need to parameterize objects with an action, queue operations, provide and do redo functionality, or log requests. The command pattern encapsulates an action as an object or function, allowing you to abstract the operation itself. Purpose: to encapsulate a request as an object or a function closure, thereby allowing clients to be parameterized with different requests, queue requests, or support undoable operations. It decouples the invoker of an operation from the object that knows how to perform the operation. Go implementation. In Go, this typically involves defining a command interface with a single execution method, e.g., execute, error. Concrete command types then implement this interface. These concrete commands often hold a reference to a receiver object that performs the actual work. Go's first-class functions also mean that a simple func error can often serve as a command or be wrapped into a command interface implementation. Conceptual example: consider a simple text editor. You might have buttons for copy, paste, save, and bold. Each button, when clicked, needs to perform a specific action on the editor's document. Instead of having the button directly call methods on the document object, each button can be associated with a command object, e.g., copy command, paste command, save command, bold command. When the button is clicked, it simply calls execute on its associated command. Each command object would hold a reference to the document, the receiver, and then implement its specific action. For undo-redo, each executed command could be pushed onto a history stack, and undo methods could be added to reverse their effects. Benefit: the command pattern decouples the invoker of an operation from the object that knows how to perform it. This provides flexibility, supports queuing and logging of requests, and enables the implementation of undo-redo functionality. 6.4 Iterator Pattern. When you have a collection of objects, like a list, tree, or graph, and you want to access its elements sequentially without exposing the underlying internal structure, the iterator pattern comes in handy. Purpose: to provide a way to access the elements of an aggregate object, like a collection or data structure, sequentially without exposing its underlying internal representation. This allows for different traversal algorithms and abstracts away the specifics of the data structure. Go implementation. While Go's built in for range loop efficiently handles iteration for slices, maps, and arrays, explicit iterators are valuable for complex or custom data structures, e.g., trees, linked lists, or large data streams. This can be done by defining an interface, e.g., iterator with hasNext, bool, and next. Item interface. Methods. For concurrent or streaming scenarios, using a channel to emit elements as they become available is a very idiomatic Go approach. Conceptual example. Imagine you've built a custom balanced binary search tree, and you want to allow users to traverse its elements in various orders, in order, pre-order, post-order, without exposing the tree's node structure. You could provide a method on the tree like new in order iterator. This method would return an object that implements the iterator interface. The client would then use a for iterator hasNext, item equals iterator next, loop to walk through the elements. For potentially large or asynchronous data sources, a function could return a channel. Func streamlines, reader IO reader, chan string. Lines equals make chan string. Go func, defer close, lines. Scanner equals bufionu scanner, reader. For scanner scan, lines scanner text, return lines. A client could then for line equals range stream lines, my file reader, /process line. Benefit: the iterator pattern decouples the traversal logic from the data structure itself, allowing for different traversal algorithms. It provides a uniform interface for accessing elements across different aggregate types, promoting abstraction and flexibility. Chapter 7. Concurrency Patterns in Go. Go's built-in concurrency, primitives, goroutines, and channels are perhaps its most celebrated features. They simplify what is often a notoriously complex area of programming. However, simply using Go and make, chan, is not enough. To build truly robust, scalable, and maintainable concurrent applications, you need to understand and apply well-established concurrency patterns. These patterns provide blueprints for using Go's primitives effectively to solve common problems in parallel computing. 7.1 Fan-out/fan-in. A common scenario in concurrent programming is needing to process a large number of independent items, where each item can be handled in parallel. Once all items are processed, their results need to be collected or aggregated. This problem is elegantly solved by the fan-out/fan-in pattern. Purpose: to efficiently process a large number of work items concurrently, leveraging multiple CPU cores or parallel I/O, and then consolidate their individual results. How it works in Go: fan-out, you typically have an input channel supplying the initial work items. A set number of worker goroutines, or workers launched per item, are spawned. Each worker reads from this input channel, performs its assigned task independently, and then sends its result to a shared output channel. Fan-in, a separate goroutine, or the main application thread, is responsible for collecting all results from the shared output channel. To ensure that all workers have completed their tasks and all results have been collected before proceeding, a sync-wait group is commonly used. The wait group ensures that the collection phase waits until all fanned-out goroutines signal they are done. Conceptual example: imagine you have a massive list of images that need to be resized and watermarked. Instead of processing them sequentially, you could fan out the work. Feed image paths into an input channel. Launch several image processing goroutines, each reading from the input channel. Each processing goroutine transforms an image and sends the path to the transformed image to an output channel. A final collector, goroutine, gathers all transformed image paths from the output channel. This approach significantly speeds up the entire operation by distributing the workload. Benefit: this pattern excels at maximizing throughput for independent computational tasks or I/O-bound operations. It effectively utilizes available processing power and manages the flow of data through concurrent stages. 7.2 Worker pools. While the fan-out fan-in pattern is great for maximizing parallelism, sometimes you need to control the degree of concurrency to avoid overwhelming system resources, like CPU, memory, database connections, or external API rate limits. This is where the worker pool pattern comes into play. Purpose: to limit the number of active goroutines performing tasks concurrently. It manages a fixed set of worker goroutines that can accept and process tasks from a queue. How it works in Go: you typically start a fixed number of goroutines, the workers, at the beginning. These workers all listen for jobs on a shared buffered channel. When a job needs to be processed, it's sent to this job channel. If the channel is full, the sender will block until a worker is free to take a job. Workers receive a job from the channel, process it, and optionally send any results to a separate results channel. Conceptual example: consider a web server that receives many requests, each of which might involve a CPU-intensive computation or a set of database queries. If you launch a new goroutine for every single request without limit, you risk exhausting your database connection pool or saturating your CPU with excessive context switching. A worker pool would pre-launch, say, 10 request handler goroutines. Incoming requests are placed into a job queue, a buffered channel. Only these 10 goroutines will ever actively process requests, ensuring your system remains stable and responsive under heavy load. Benefit: worker pools ensure controlled concurrency, preventing resource exhaustion and improving system stability. They smooth out bursts of requests, making your application more predictable and resilient. 7.3 Pipelines. Software often involves processing streams of data through a series of transformations. Think of a chain of tasks where the output of one step becomes the input for the next. This sequential processing through stages is perfectly suited for the pipeline pattern. Purpose: to process a stream of data through a series of sequential stages, where each stage performs a specific transformation or computation. Each stage runs in its own goroutine and communicates with adjacent stages using channels. How it works in Go: each stage in the pipeline is implemented as a goroutine. An input channel feeds data into the first stage. Each subsequent stage reads from its input channel, which is the output channel of the previous stage, and writes its processed output to its own output channel. Data flows downstream through these connected channels. Conceptual example: imagine building an application that processes raw log entries. Stage 1, Reader. A goroutine reads lines from a log file and sends them to a raw logs channel. Stage 2, Parser. A goroutine reads from raw logs, parses each line into a structured log entry, and sends the structured entry to a parsed logs channel. Stage 3, Filter. A goroutine reads from parsed logs, filters out irrelevant entries, and sends important ones to a filter-read logs channel. Stage 4, Writer. A goroutine reads from filter-read logs and writes them to a database or another file. Each stage operates concurrently. As soon as the reader produces a line, the parser can start working on it, even if the reader hasn't finished reading the entire file. Benefit: pipelines promote a clear separation of concerns, as each stage has a single, well-defined responsibility. This makes the system highly modular, easy to extend. Just add a new stage or modify, change one stage without impacting others, and enables high throughput because stages can operate in parallel. 7.4 Cancellation and timeouts with context.context. In any complex application, especially distributed systems, operations might take too long, become irrelevant, or need to be stopped gracefully. Blocking indefinitely can lead to resource exhaustion and an unresponsive application. Go's context.context is the standard for managing these scenarios. Purpose: to gracefully signal cancellation, timeouts, or deadlines to individual operations or an entire tree of coroutines, and to propagate request-scoped values down a call chain. How it works in Go. The context.context object is typically created using functions like context with cancel, context with timeout, or context with deadline. These functions return a child context and a cancel func. The context object is passed as the very first argument to any function or coroutine that might perform a long-running operation, like network calls, database queries, or complex computations. Inside those functions or coroutines, the context's done channel is monitored, usually within a select statement. If done closes, it signals that the operation should cease. Calling the associated cancel func, or when a timeout deadline expires, triggers the closing of the done channel across all child contexts, propagating the cancellation signal. Conceptual example. Consider an API endpoint that needs to fetch data from 3 different microservices to compose a response. If the client that made the request disconnects, or if the overall request has a 5-second timeout, you want to stop all ongoing fetches and release resources. You would start the API handler with a context with timeout for the entire request. This context is then passed to the coroutines calling the individual microservices. Each coroutine monitors CTX done. If the timeout expires or the client disconnects, the parent context is canceled. It's done. Channel closes, triggering all dependent coroutines to abort their operations and return, preventing unnecessary work and resource wastage. Benefit. The context.context is absolutely vital for building robust, responsive, and resource-efficient services. It prevents coroutine leaks, allows for graceful shutdowns, and provides a clear mechanism for propagating control signals and request-specific data throughout a complex system. 7.5 Error propagation in concurrent systems. When multiple coroutines are working concurrently, errors can occur independently in any of them. The challenge then becomes how to effectively collect and handle these errors, especially if a failure in one coroutine should signal a halt to the entire operation or be reported back to a central point. Ignoring errors in concurrent operations can lead to subtle bugs and system instability. Purpose: to safely and effectively collect and handle errors that occur independently within multiple coroutines, bringing them back to a central point if needed. How it works in Go. Single error channel. A common approach is to create a dedicated error channel. Each worker coroutine, if it encounters an error, sends that error to this channel. A collector coroutine, or the main thread, then reads from this error channel, processing or aggregating the errors. This requires careful management of channel closure and potential blocking. Golang.org/x/sync/uragroup : for many common scenarios, the uragroup package, an external but widely adopted and highly recommended library, offers a much simpler and more robust solution. It provides a group that can manage a collection of coroutines and will return the first error encountered by any of them. It also seamlessly integrates with context.context for cancellation. If one coroutine returns an error, the group will cancel its associated context, signaling other coroutines to stop. Conceptual example. Imagine you need to download and process configuration files from 10 different URLs concurrently. If any of the downloads fail, or if the processing of a single file fails, you want the entire operation to stop and report the error quickly. Using uragroup, you'd create an uragroup group and then launch each download and process coroutine using ggo func error. Inside each function, if an error occurs, you simply return error. The main routine would then just call gwait. Gwait will block until all coroutines complete, and if any of them returns an error, wait will return the first error received. All other coroutines launched by that group will also receive a cancellation signal via the group's context. Benefit: effective error propagation ensures that failures in concurrent operations are not silently swallowed. It provides a structured and clear way to handle problems, making your applications more fault-tolerant and easier to debug, especially in distributed environments. Chapter 8. Writing clean, maintainable Go. Writing code that works is one thing. Writing code that is clean, readable, and easily maintainable by yourself, and others is another entirely. Go has a strong opinionated stance on code style and organization, and by embracing these conventions, you contribute to a consistent and collaborative ecosystem. This chapter delves into the practices that lead to high-quality, maintainable Go code. 8.1 Naming Conventions. Clarity is key. Go's naming conventions are designed for conciseness and clarity, often prioritizing short, meaningful names where appropriate. Adhering to these conventions is crucial for writing idiomatic Go. The most fundamental rule governs visibility. Exported public identifiers, variables, functions, types, methods must start with a capital letter. These are visible and usable outside the package they are defined in. Unexported private identifiers must start with a lowercase letter. These are only visible and usable within the package they are defined in. This simple rule makes access control explicit and immediately clear to any Go developer reading your code. For general naming, use camel case for multi-word names, e.g., max connections, new user service. For local variables and function parameters, especially those with short lifespans, Go prefers concise names. For example, I for loop counters, R for an IO reader, W for an IO writer, CTX for a context.context, and for an error value. This conciseness is balanced by the fact that these variables are used in a very limited scope, where their meaning is obvious. For exported identifiers and package-level variables, descriptive names are more important. Request timeout is better than RT. Interface names often end with if they denote a capability or an action, e.g., reader, writer, formatter, closer. This instantly communicates their purpose. Adhering to these naming conventions significantly enhances code readability and reduces cognitive load, making it easier for any Go developer to understand the structure and intent of your code. 8.2 Package Structure and Organization. Go programs are organized into packages. The way you structure these packages profoundly impacts the modularity, testability, and overall navigability of your codebase. The primary principle is small, focused packages, each with a single, clear responsibility. Avoid creating large, monolithic packages that try to do too many things. Break down large functionalities into smaller, cohesive units. For instance, rather than a single utils package that contains all sorts of unrelated helper functions, create specific packages like httputil for HTTP-related utilities or filio for file operations. A widely adopted convention is the use of the internal directory. If you create a directory named internal, e.g., yourmodule/internal/mypackage, any package within it can only be imported by code within the same module. The Go compiler strictly enforces this. This is extremely useful for encapsulating implementation details and defining clear architectural boundaries, preventing external consumers of your module from depending on code that is not part of your public API. Dependency direction is also important. Design your packages so that common utilities and foundational services are at the bottom of the dependency graph, with more application-specific logic built on top. This creates a clear flow of dependencies and avoids complex circular relationships. Go strictly forbids circular imports, where package A imports package B and package B imports package A, a design choice that actively forces better modularity and reduced coupling. While flexible, many Go projects adopt a common layout for larger applications. CMD/ contains main packages for executable applications. Each subdirectory here is a separate executable. PKG/ contains library code that may be used by external applications or packages. API/ defines API specifications, e.g., protobuf definitions, open API specs. Internal. As discussed, for private module-specific code, this logical organization improves both maintainability and teamwork by providing a predictable structure. 8.3 Comments and Documentation, Go Doc. While readable code is paramount, effective documentation clarifies intent and usage. Go integrates documentation directly with your code through its unique commenting style and the Go Doc tool. When to comment, why, not what. Avoid commenting on obvious code, e.g., loop through elements. Instead, explain why a particular piece of complex logic exists, what assumptions it makes, or what side effects it might have. Public APIs, every exported, capitalized, type, function, method, and variable should have a documentation comment directly preceding its declaration. These comments are parsed by GoDoc and used to generate readable API documentation, e.g., on pkg.go.dev. Examples. Go allows you to include example functions within your test.go files, e.g., func example my function. These examples demonstrate how to use your exported elements, are verified as part of GoTest, and are displayed in the generated documentation. This ensures your examples are always correct and up to date. Proper documentation helps reduce the onboarding time for new developers and ensures that the API's intended use is clear, promoting correct usage. 8.4 Testing and Benchmarking. Go has robust, first-class support for testing and benchmarking directly within its toolchain, encouraging a strong testing culture. Tests are placed in files ending with test.go, typically within the same package as the code they test. Unit tests. Functions starting with func test xxx, testing t, are executed as unit tests. They focus on testing individual functions or components in isolation. Table-driven tests, a highly idiomatic and efficient way to write many unit tests in Go. You define a slice of test cases, each containing input data and expected output, and then loop through them, applying the same test logic to each case. This dramatically reduces boilerplate code for tests. Integration tests, often placed in a separate test.go file within a package named test, e.g., myPackageTest, to ensure they only test the public API and don't introduce circular dependencies. These test how different parts of your system interact. Test doubles. Go's strong interface system makes creating test doubles, mocks, stubs, fakes, very straightforward. You simply define an interface for a dependency and create a mock type that implements that interface for testing purposes. Complex mocking frameworks are rarely needed. Benchmarking is built directly into the testing framework. Functions starting with func benchmark xxx, b testing b, measure the performance of code. You run them using GoTest bench equals. The bn loop is critical here, as the benchmarking harness adjusts bn to ensure stable measurement times. A strong test suite ensures correctness, prevents regressions, helps in understanding code behavior, and identifies performance bottlenecks early. 8.5 Code formatting, Go FMT, and linting, Go vet, Galling silent. Go's commitment to consistency extends to code style, largely enforced by automated tools. Go FMT. This is the ultimate arbiter of Go code style. It automatically formats your Go source code according to the official Go style guide. The beauty of Go FMT is that it eliminates debates over stylistic choices among developers. All Go code across all projects tends to look identical, which greatly improves readability and consistency. You should run Go FMT automatically, Go FMT, before every commit. Go vet. This static analysis tool, built into the Go distribution, helps find suspicious constructs in your code that are likely programming errors. Examples include unused variables, misuses of format strings in print functions, or unkeyed struct literals. It catches potential bugs that the compiler might miss. Galling silent. While GoVet is useful, the Galling silent tool is a popular meta-linter that aggregates a vast collection of other static analysis tools, linters for Go. It can enforce additional stylistic guidelines, detect more nuanced potential bugs, identify performance issues, and spot security vulnerabilities. E.g., staticec, revive, gosic. Using a comprehensive linter like Galling silent as part of your continuous integration. CI, pipeline, is a highly recommended best practice. These tools automate code consistency and quality checks, reducing manual review effort and catching common errors and potential performance issues during the development phase, long before they become bugs in production. Embracing them frees developers to focus on the logic, knowing the style is handled. Chapter 9. Robust error handling and observability. Building reliable and high-performance software requires more than just writing functional code. It demands a proactive approach to handling errors and gaining deep insights into your application's behavior. This is where robust error handling and observability become paramount. Observability, The ability to understand the internal state of a system by examining its outputs is achieved through good logging, metrics, and tracing. 9.1 Advanced Error Handling. Context and semantics. The explicit if equals nil check is fundamental to Go's error handling. While simple, it forms the basis for a more sophisticated strategy. Error values versus error types. In Go, an error is an interface. For basic known conditions, you can simply return constant, sentinel errors, like the IOEOF error, which signals the end of a file. These are simple values, and you check them directly with errors. Is. However, for more complex scenarios or when you need to convey additional structured information about what went wrong, you can define custom error struct types. These custom types must implement the error string method, which returns the error message. They can embed extra fields like an error code, details, or user message, offering richer contextual information than a plain string. Error wrapping and unwrapping. Blindly returning up the call stack without adding context is a common anti-pattern, which we'll discuss later. Instead, you should enrich errors with contextual information using error wrapping. Go's FMT error with the %w verb allows you to wrap an original error. For example, FMT error failed to process request. %w, originaler, means you're adding a human-readable explanation of where the error occurred while simultaneously preserving a link back to the originaler. This creates a chain of errors, preserving the deeper cause. To intelligently inspect these wrapped error chains, the errors package provides two crucial functions. Errors is error targeter. This checks if a given error is or wraps a specific target error value, like IOEOF, anywhere in its chain. It's often used to determine if a specific known error condition occurred, regardless of how many layers of context it's wrapped in. Errors as error and target var. This checks if an error is or wraps a specific type of error. If it does, it unwraps the error from the chain and assigns it to target var, which must be a pointer to an error type. This is invaluable for retrieving structured data from custom error types you've defined, allowing you to react to the semantic meaning of an error. By embracing error wrapping and using errors, as you enable both generic error handling, if equals nil, and specific, semantically rich error handling, providing far better context for debugging and making your error handling code more precise and maintainable. 9.2 Logging strategies. Logs are the breadcrumbs your application leaves behind, helping you understand its journey. Effective logging is paramount for debugging, troubleshooting, and monitoring in production. Structured logging. Traditional log messages are often free-form strings, making them difficult for machines to parse efficiently. Structured logging solves this by outputting logs as machine-readable key-value pairs, typically in JSON format. This format is ideal for log aggregation and analysis tools, like Elastic-Stack, Splunk, or Datadog, allowing for powerful querying, filtering, and visualization. As of Go 1.21, the new log-slog package is the official, built-in solution for structured, leveled logging. It provides a simple yet powerful API to generate logs that are easy for both humans and machines to understand. Logging levels. Logs should be categorized by severity levels to help focus attention on critical issues. Common levels include debug, highly granular information, useful for development or deep troubleshooting when diagnosing specific problems. Info, general operational insights, significant events, or successful completions. This is typically the default level in production. Warning, unusual or unexpected events that might indicate a problem but don't prevent normal operation, e.g., a non-critical external service is slow. Error, critical failures that prevent an operation from completing successfully. These usually require attention. Crit/fatal, events that indicate the application is in an unrecoverable state and might need to shut down. Contextual logging. One of the most important aspects of logging, especially in microservices architectures, is contextual logging. This involves automatically attaching relevant context to all log entries related to a specific operation or request. Examples include request ID, a unique identifier for an incoming request, allowing you to trace all logs generated across multiple services for that one request. User ID. Identifying the user associated with an operation. Trace ID. Linking logs to a distributed trace, discussed next. Session ID, transaction ID, etc. Propagating these values is typically done via context.context, embedding them into the context, and allowing the logger to extract and automatically include them in log records. Benefit: structured, contextual, and leveled logging significantly improves debuggability, provides clear operational visibility, speeds up incident response, and helps you understand how your application behaves in production. 9.3 Metrics and telemetry. While logs tell a story of discrete events, metrics provide aggregated, numerical measurements of your system's behavior over time. They are essential for understanding system health, performance trends, and for creating dashboards and alerts. Basic metrics types. Counters, monotonically increasing numerical values. They represent a count of occurrences, e.g., total HTTP requests served, number of errors, count of messages processed. They only ever go up. Gauges represents a single numerical value that can go up or down. They show the current state of something, e.g., current number of active coroutines, CPU utilization, queue size, temperature. Histograms/summaries, used to represent distributions of observed values over time, e.g., request latency, response body size, database query duration. They record observations and provide statistical insights like counts, sums, and quantiles, e.g., 90th percentile, 99th percentile latency. Using Prometheus. The Prometheus monitoring system has become a de facto standard for collecting metrics in cloud-native environments. Go applications often use the github.com/prometheus/client_galling library to instrument their code. This library provides easy-to-use APIs for defining and incrementing counters, setting gauge values, and observing histogram measures. Prometheus servers then pull these metrics from your application endpoints, store them, and allow for powerful querying and visualization, often with Grafana. Benefit: metrics provide real-time and historical insights into application health and performance. They enable proactive issue detection, e.g., alerting when latency spikes, facilitate capacity planning, and help identify long-term performance degradation trends, moving you from reactive firefighting to proactive management. 9.4 Tracing for distributed systems. In monolithic applications, correlating logs and metrics for a single user request is relatively straightforward. However, in a distributed system, like microservices, a single user request might traverse dozens of services, each generating its own logs and metrics. This makes diagnosing latency issues or failures incredibly challenging. This is where distributed tracing shines. Understanding distributed traces. A trace represents the end-to-end journey of a single request or operation through a distributed system. It's composed of multiple spans. Each span is a single operation, e.g., an RPC call, a function execution, a database query, or even just processing within a service. Spans are nested, forming a tree-like structure that describes the causal relationships and timing of operations within a trace. For example, a trace might start with an incoming HTTP request. The first span covers the web server. That span might then contain child spans for a call to an authentication service, a call to a data service, and a database query, all occurring within the context of that original request. OpenTelemetry. OpenTelemetry has emerged as the industry standard, vendor-neutral framework for generating, collecting, and exporting telemetry data, traces, metrics, and logs. It provides a unified set of APIs, SDKs, and tools across different programming languages. Its adoption ensures that your Go application's instrumentation can integrate seamlessly with various tracing backends, like Jaeger, Zipkin, Datadog, or Honeycomb. The crucial aspect of distributed tracing is trace context propagation. This means that a unique trace ID and current span ID are passed from one service to the next, typically via HTTP headers or message queue headers. This allows all the individual spans generated by different services to be correctly linked together into a single, cohesive trace. Go's context.context is the ideal mechanism for carrying and propagating this trace context within a service. Benefit: Distributed tracing is absolutely essential for debugging performance bottlenecks and failures in complex, interdependent systems. It allows you to visualize the entire lifecycle of a request, pinpointing exactly which service, or even which internal function within a service, is causing delays or leading to errors. Think of it as a breadcrumb trail that follows a single user's request through your entire system, showing where it went, what it did, and how long each step took. Chapter 10. Performance and Optimization. While Go is known for its performance characteristics, simply writing Go code doesn't magically make it fast. Understanding where your application spends its time and resources is crucial for effective optimization. Premature optimization is a well-known pitfall. It involves spending time optimizing code that isn't a bottleneck, often at the expense of readability and maintainability. The key to successful optimization is to be data-driven, which means profiling your application. 10.1 Profiling Go Applications, pprof. Go comes with powerful, built-in profiling tools accessible through the runtime/pprof and net/http/pprof packages. The pprof package enables you to collect and analyze various types of profile data, pinpointing exactly where your application is consuming resources. Types of profiles. CPU profile. This profile identifies the functions or code paths where your CPU spends most of its time executing. It's the go-to profile for finding CPU-bound bottlenecks. It samples your program's call stack periodically. Memory profile, allocspace, in usespace. This tracks memory allocations and usage patterns. Allocspace shows the total memory allocated during the profiling period, regardless of whether it was later freed. Useful for identifying functions that cause excessive temporary allocations, which stress the garbage collector. In usespace shows the memory currently in use by live objects at the time of the profile. This helps find true memory leaks or objects holding onto large amounts of memory. Block profile. This helps identify goroutines that are blocked for significant periods, waiting on shared resources, e.g., mutexes, channel operations, I/O. If your program benefits from concurrency but isn't achieving the expected speedup, block profiling can reveal serialization bottlenecks. Goroutine profile. This lists all active goroutines and their stack traces. It's invaluable for finding goroutine leaks, goroutines that never terminate, or unexpectedly high numbers of goroutines. Mutex profile. Similar to block profile, but specifically highlights goroutines waiting on sync mutex contention. Using pprof, you typically enable profiling by importing net/http/pprof in your main package. Import net/http/pprof. Import for side effects registers HTTP handlers. In your main function or somewhere, start an HTTP server. Go HTTP listen and serve, localhost :6060, nil. Then, you can access profiles by visiting http localhost :6060/debug/pprof/ in your browser. To get a specific profile, you can download it, e.g., http localhost :6060/debug/pprof/heap ? Debug equals 1 for raw memory data. To analyze profiling data, you use the go tool pprof command. For instance, to analyze a CPU profile collected from a running service, go tool pprof http localhost :6060/debug/pprof/profile. This will block for 30 seconds to collect the data. Go tool pprof provides an interactive command line interface where you can type commands like top, shows top end functions by samples. List function name shows source code for function with samples annotated. Web generates a call graph in your browser, or SVG for a flame graph. Benefit: pprof enables precise identification of performance bottlenecks, ensuring that optimization efforts are targeted and effective. It's like having a thermal camera for your code, showing exactly where the most heat work is being generated. 10.2 Common performance pitfalls. Certain coding patterns or design choices can inadvertently lead to performance issues in Go. Being aware of these pitfalls can help you write more performant code from the outset. Excessive allocations and garbage collection, GC, pressure. Every time memory is allocated on the heap, e.g., creating a new slice, map, string, or struct instance. The Go garbage collector eventually needs to clean it up. Frequent small allocations can lead to significant GC overhead, impacting performance as the GC pauses your program or consumes CPU cycles. String concatenation with plus. When concatenating many strings using the plus operator, Go creates many intermediate, immutable string copies. This can be significantly inefficient, especially within loops, due to repeated memory allocations and copying. Unnecessary I/O operations. Disk or network I/O operations are inherently orders of magnitude slower than in-memory operations. Repeatedly reading from disk, making redundant network calls, or performing unbuffered I/O can be major bottlenecks. Inefficient data structures or algorithms. Choosing a data structure or algorithm that is suboptimal for the problem at hand, e.g., using a linear search on a large slice where a hash map lookup, O1, would be more efficient, or using bubble sort for a large dataset. Lock contention. In concurrent code, if multiple goroutines frequently try to acquire the same mutex or send-receive on a heavily contended channel, much of the concurrency benefit can be lost. Goroutines spend time waiting for each other, effectively serializing execution even if you have many CPU cores. The block and mutex profiles help identify this. Goroutine leaks. As discussed in Chapter 7, goroutines that never terminate continue consuming memory and CPU, leading to slow, memory-hungry applications and eventual crashes. 10.3 Optimization Techniques. Once you've identified a bottleneck using pprof, you can apply specific optimization techniques. Remember to always benchmark changes to objectively verify actual performance improvements. Optimizations often have unintended consequences or yield negligible gains if not data-driven. Pooling objects, sync pool. For frequently created, short-lived, and identical objects, e.g., byte buffers for network I/O, sync pool allows reusing objects instead of allocating new ones each time. This significantly reduces GC pressure, as objects can be picked from the pool and later returned, rather than being garbage collected. Pre-allocating slices and maps. When the approximate capacity of a slice or map is known beforehand, use make T0 capacity for slices and make mapkv capacity for maps. This pre-allocates the underlying memory, avoiding costly reallocations and data copying as elements are added, especially in loops. Efficient string building. For concatenating many strings, especially within loops, always use strings builder for string output or bytes buffer for byte slice output. These types provide efficient, mutable buffers that minimize allocations. Leveraging efficient standard library functions. Go's standard library is highly optimized. Before writing custom string manipulation, byte processing, or sorting logic, check if packages like bytes, SDRconv, sort, or IO offer a more performant and idiomatic way. For JSON, prefer JSON encoder and JSON.decoder for streaming I/O over JSON Marshall and JSON and Marshall for large data structures to reduce memory footprint. Avoiding global locks, fine-grained locking. Instead of locking entire sections of code or large data structures, identify the smallest possible critical section and lock only the necessary data. This increases parallelism and reduces contention. Consider syncrw mutex if you have many readers and few writers. Tune GC settings. In very specific high-performance scenarios, tuning the GOGC environment variable can help by adjusting the garbage collector's aggressiveness. However, this is advanced, usually not necessary, and should only be done after extensive profiling. Careful use of unsafe and CGO. These packages offer direct memory manipulation or C interoperability for extreme performance needs. While they can provide significant speedups in very specialized cases, they compromise Go's safety, portability, and readability. Their use should be approached with extreme caution, and only when thoroughly benchmarked and verified that standard Go approaches are insufficient. By systematically profiling your application and applying these targeted optimization techniques, you can ensure that your Go programs not only function correctly, but also meet their performance requirements efficiently. Remember, measure, then optimize. Chapter 11, Common Go Anti-Patterns. Just as there are best practices and effective patterns, there are also anti-patterns. Common solutions to recurring problems that are, in fact, ineffective and can lead to bad design, increased complexity, and harder maintenance. Understanding and recognizing these anti-patterns is as crucial as knowing the good patterns, helping you steer clear of pitfalls and write more robust, idiomatic Go code. 11.1 The error catch-all. If equals nil, return nil, Go's explicit error handling is a powerful feature, but its simplicity can sometimes lead to a common anti-pattern, blindly propagating errors without adding any context. Anti-pattern, func get data, byte error. Data equals read from file, config txt. If equals nil, anti-pattern, just returning the error as is. Return nil, Return data, nil. Problem: this seemingly harmless approach makes debugging incredibly difficult in a larger application. When an error eventually bubbles up to the top level, its original meaning and the specific point of failure are lost within a generic message like file not found. You won't know which file was not found, or in the context of what broader operation the failure occurred. Such an error message provides no actionable insight. Solution: always enrich errors with context using fmterrorf. Meaningful message about failed operation X, %w, The %w verb is key here, as it wraps the original error, creating a chain of errors. This allows you to retain the original error's information while adding valuable context about where the error was encountered and why it matters in that specific part of the code. Corrected example: import fmt us func read from file filename string byte error. Data equals os read file filename. If equals nil, return nil fmterrorf. Failed to read file %q. %w filename Return data nil. Func get data byte error. Data equals read from file config txt. If equals nil, enriched error tells you what high-level operation failed. Return nil fmterrorf. Failed to retrieve configuration data. %w Return data nil. Now, if config txt is not found, the error at get data will intelligently communicate something like failed to retrieve configuration data, failed to read file config txt, no such file or directory. This provides a clear, traceable path to the root cause. You can then use errors, is, and errors as at higher levels to check for specific error conditions in this chain. 11.2 Overusing the empty interface, or any. The empty interface, now aliased as any since Go 1.18, can hold a value of any type. While powerful and sometimes necessary, its overuse is a classic anti-pattern in Go. Anti-pattern, type processor struct. Data store map string interface, storing heterogeneous data. Func p processor process input interface, error. Complex type assertions and switches. Problem: relying too heavily on interface. Bypasses Go static type safety checks. This means the compiler cannot catch type-related mistakes, pushing them to runtime. You end up with verbose and error-prone type assertions, type, and type switches. A wrong assumption about the underlying type can lead to a panic at runtime, which is highly undesirable. It makes code harder to read, debug, and maintain, as the type constraints are hidden. Solution: prefer specific, small interfaces. Use interfaces that define specific behaviors or contracts rather than a catch-all solution. This allows you to leverage Go's type system effectively. Leverage Go generics, Go 1.18+. For truly generic data structures or algorithms where any might have been used in the past, generics type parameters provide a compile-time safe solution. They allow you to write algorithms that operate on types specified by the caller, without losing type safety. Handle type assertions carefully. When any is genuinely necessary, e.g., when working with JSON payloads where types are inherently dynamic or in reflection-heavy code, always use the OK idiom for type assertions, val OK data. Concrete type. If OK/handle type mismatch, the improved approach with generics. Using generics for a type-safe, generic container. Type cachek comparable, v any struct. Data store map kv. Func c cachek v, get key k, v bool. Val OK equals c data store key. Return val, OK. Generics provide runtime safety by enforcing type constraints at compile time, reducing the need for any in many scenarios where type flexibility is required. 11.3 Global State Abuse. Global state refers to data that is accessible and mutable from anywhere in your application without explicit passing. While convenient, over-reliance on global state is a significant anti-pattern. Anti-pattern, in package config, var database URL string, var API max retries int, func load config, called once at startup, database URL equals os_getenv, derail, API max retries equals sdrconvat, os_getenv, apyretres. In package database, import my/app/config, uses config database URL directly. Problem: reduced testability. Components become tightly coupled and impossible to test in isolation without manipulating the global state. Tests can influence each other through shared state. Hidden dependencies. It becomes unclear which parts of the code rely on or modify which pieces of global data. This creates spaghetti code. Concurrency issues. In concurrent environments, mutable global state is a major source of race conditions if not meticulously protected with locks. Lower reusability. If a package relies on global state, it's difficult to reuse that package in another context where the global state might be configured differently. Solution: prefer dependency injection. Pass dependencies, configurations, database connections, service clients, explicitly as function arguments or, more commonly, as fields within structs. This makes dependencies clear and allows for easy swapping of implementations, e.g., for testing. For immutable configuration. If configuration is truly immutable after initialization, a package-level variable initialized with sync once might be acceptable, but it's still best to pass even configuration structs around. Protect mutable shared state. If you absolutely must have mutable shared state, which should be rare, protect it diligently with sync mutex or channels for concurrent access. Improved approach: dependency injection. Type config struct, database URL string, API max retries int. Type database client struct, constring string. Func new database client, CFG config, database client error. Uses config passed explicitly. Return and database client constring. CFG database URL, nil. Type service struct, DB database client. Func new service, DB database client service. Return and service DB, DB. In main, func main, CFG equals config. Database URL, os_getenv, derail. DB client equals new database client, CFG. My service, new service, DB client. This explicit approach makes dependencies transparent, improves testability, and reduces side effects. 11.4 Package name collision and overlap. Poor package naming and organization can lead to confusing imports and a messy codebase, hindering discoverability and clarity. Anti-pattern. Creating highly generic packages like util, common, helpers, types, or models that become dumping grounds for unrelated functions and definitions. Having different packages that end up with the same effective name or functionality when imported, requiring developers to use awkward import aliases, e.g., import client, github.com/myorg/api/client, and import other client, github.com/otherorg/otherapy/client. Problem: break single responsibility principle. Packages should have a single, clear purpose. Generic names hide this. Confusing imports. Import my/app/util tells you nothing specific about what it contains. Ambiguity. Client new request might be ambiguous if you have multiple client packages. Hard to discover. New developers struggle to find where functionality resides. Solution: design packages around distinct, cohesive responsibilities. Give them clear, meaningful, and unique names that reflect their purpose or the domain concept they represent. Good examples: HTTPutil, IOUTIL, SQLutil for context-specific utilities. User order product for domain models and logic. Auth middleware, storage for functional modules. Go's typical package name should be a short, single lowercase word. The package name also affects how you use its exported members, e.g., user new user, order place order. Choosing a good name makes your API self-documenting. 11.5. Neglecting context.context. Failing to properly use context.context for cancellation, timeouts, and value propagation is a severe anti-pattern, especially in network services and long-running operations. Anti-pattern, func fetch data from external service, byte error, performs a long-running HTTP request or DB query. No context passed or checked. Resp equals HTTP get, HTTP / external service / data. This will block indefinitely. Problem, resource leaks. Goroutines perform operations that might never complete, leading to goroutine leaks, memory consumption, and unresponsiveness. Uncontrolled timeouts. Operations can block indefinitely, causing cascading failures in distributed systems. Lack of control. You cannot signal a long-running operation to stop gracefully if the upstream caller cancels or times out. No value propagation. Crucial request scoped values, like trace IDs, authentication tokens, user IDs, cannot be easily passed down the call chain. Solution. Always accept context.context as the very first argument to functions that might perform I/O, interact with external systems, or involve long-running computations. Inside these functions, monitor CTX done, using a select statement to react to cancellation or timeout signals. Corrected example. Import, context, FMT, EO/IOTIL, net/HTTP. Time, func fetch data from external service, CTX context.context, URL string, byte error. Rec equals HTTP new request with context, CTX, get URL nil. If equals nil, return nil, FMT error, failed to create request. %w client equals an HTTP client. Consider reusing this client. Resp equals client do rec. If equals nil, HTTP clients do handles context cancellation, returning an error. Return nil, FMT error, failed to make HTTP request. %w defer resp body close. Data equals IOTIL read all resp body. If equals nil, return nil, FMT error, failed to read response body. %w return data nil. Func get remote config, CTX context.context, byte error. Create a context specifically for this operation with a timeout. CTX cancel equals context with timeout. CTX 5 * time second. Defer cancel. Always call cancel for any with cancel, with timeout, with deadline. Data equals fetch data from external service, CTX, HTTP //config service /latest. If equals nil, return nil, FMT error, could not fetch remote config. %w return data nil. By consistently passing and respecting contexts, your Go applications become more robust, responsive, and observable, preventing common issues related to resource management and request lifecycle. Chapter 12, Pitfalls in Concurrent Go. While Go makes concurrent programming significantly easier and safer than many other languages, it doesn't eliminate all the complexities. When working with goroutines and channels, it's crucial to be aware of and actively guard against common concurrency pitfalls. These issues can lead to subtle bugs that are notoriously difficult to reproduce and debug. 12.1 Race Conditions. A race condition occurs when multiple goroutines access shared memory concurrently, and at least one of the accesses is a write operation without any proper synchronization. The final outcome then becomes dependent on the unpredictable interleaving of operations. Because the timing of goroutines is non-deterministic, the bug might only manifest intermittently, making it extremely hard to diagnose. Problem: imagine two goroutines simultaneously trying to increment a shared counter without protection. Goroutine A reads the counter, value 5. Goroutine B reads the counter, value 5. Goroutine A increments its local copy, value 6, and writes it back to shared memory. Goroutine B increments its local copy, value 6, and writes it back to shared memory. The expected result is 7, but the final value stored is 6 because goroutine B overwrote goroutine A's update. Identifying race conditions. Go provides an invaluable tool to detect race conditions. The race detector. You can enable it by running your tests or application with the race flag, go run race mango. Go build race mango. Go test race. The race detector instruments your code to observe memory access patterns and will report any detected race conditions. You should always run your tests with the race detector enabled in your CI/CD pipeline. Solutions for race conditions: mutexes, sync mutex, syncrw mutex. The most common solution for protecting shared data. A sync mutex ensures that only one goroutine can execute a critical section of code at a time. Syncrw mutex provides a reader-writer lock, allowing multiple readers concurrently, but only one writer or one writer exclusively. Channels goes preferred approach outlined in its concurrency philosophy. Don't communicate by sharing memory. Share memory by communicating. By passing data between goroutines using channels, you simplify synchronization because the data itself is owned by a single goroutine at any given time, or its transfer is explicitly synchronized by the channel's send-receive operations. Atomic operations, sync atomic. For simple, single-word operations, like incrementing an integer, adding to a value, or swapping pointers, the sync atomic package provides highly optimized, low-level instructions that guarantee atomicity without requiring a heavier mutex. They are suitable for simple counters or flags. 12.2 Deadlocks. A deadlock occurs when two or more goroutines are blocked indefinitely, each waiting for a resource that is held by another goroutine in the same blockage. The system grinds to a halt because no goroutine can proceed. Problem: imagine two goroutines needing to acquire two different locks to complete their task. Goroutine A acquires lock 1. Goroutine B acquires lock 2. Goroutine A tries to acquire lock 2, but it's held by B SOA blocks. Goroutine B tries to acquire lock 1, but it's held by A SO B blocks. Both goroutines are now waiting for each other, and neither can release the lock the other needs. Total gridlock. Common causes of deadlocks: circular waiting, the scenario described above. Forgotten unlock calls. A mutex is locked but never released, often due to an early return or a panic before defer mu unlock. Unbuffered channel misuse. Sending to an unbuffered channel when no receiver is ready, or receiving from one when no sender is ready. If both the sender and receiver are within the same blocked goroutine, it's a deadlock. Sync-wait group misuse. If add calls are not matched by done calls, or wait is called before all goroutines are launched, the wait might block indefinitely. Strategies to avoid deadlocks. Consistent locking order. Always acquire multiple locks in the same predefined order across your entire application. This eliminates circular waiting. Timeouts and cancellation. Context. Use context with timeout on blocking operations, e.g., channel sends receives, database calls, external API requests. This prevents indefinite waits and allows operations to fail gracefully rather than deadlock. Buffered channels. Use buffered channels when producers and consumers don't need strict, immediate synchronization. This allows some decoupling and prevents blocking until the buffer is full. Avoid nested locks. Minimize situations where one mutex is acquired while another is already held, as this significantly increases the risk of circular dependencies. Careful design. Thoroughly design and review the interaction flows between goroutines, especially around shared resources. 12.3 Goroutine leaks. A goroutine leak occurs when a goroutine is started but never exits, continuing to consume system resources, memory, CPU, file handles, network connections, indefinitely. Over time, these accumulated, defunct goroutines can lead to performance degradation, memory exhaustion, and eventual application crashes. Problem: a common scenario is a goroutine reading from a channel that never receives any more data and never gets closed. The goroutine simply waits forever. Or a goroutine sending to an unbuffered or full buffered channel where no one is reading. Example scenario: leak, func leaky worker, ch-chan int. This goroutine waits indefinitely if ch is never closed or sent to. Func main, ch equals make chan int. Go leaky worker, ch. No one sends to ch, and ch is never closed. Leaky worker stays alive. Detection. The Go tool pprof's goroutine profile is the primary tool for detecting leaks. It lists all active goroutines and their stack traces, making it easy to spot goroutines that are unexpectedly stuck or lingering. Solutions for goroutine leaks. Clear exit conditions. Ensure all goroutines have defined exit conditions. For long-running or potentially cancelable operations, always use select with context done. To allow graceful termination when a parent operation is canceled or times out. Close channels. When a channel is no longer needed or all sending is done, close it. This allows receivers to unblock and exit their loops. Be careful not to close a channel that other goroutines might still send values to. Handle all sends receives. If you have an unbuffered channel, ensure there's always a sender for every receiver and vice versa, or use timeouts. For buffered channels, be mindful of buffer capacity. Sync-wait group. Use sync-wait group to ensure that you wait for launched goroutines to complete their work, validating that they've exited as expected. 12.4 Starvation. While less common than deadlocks in typical Go applications due to Go's MN scheduler, starvation occurs when a goroutine is repeatedly denied access to a shared resource or CPU time, even though it's ready to run. It gets starved of what it needs to progress. Problem: a goroutine might continuously lose in contention for a mutex or channel access against other, faster, or more frequently scheduled goroutines. It's technically runnable, but it just never gets a chance to make progress. Distinction from deadlock. In starvation, the goroutine is technically able to run, not blocked indefinitely by another's resource, but it just never gets scheduled or always loses the race for a resource. In a deadlock, the goroutine is truly blocked, unable to do anything. Causes: highly contended resources where the scheduling or locking mechanism is unfair. Complex priority systems that always favor certain goroutines. Busy waiting loops that consume CPU without yielding, preventing other goroutines from running. Solutions: avoid busy waiting, spinning on a condition without yielding control. If you're waiting for a condition to be met, use channels or sync.cond to signal when the condition is ready. Monitor goroutine activity and resource contention in production, e.g., using block and mutex profiles. Go's runtime scheduler is generally fair, so explicit starvation requires specific, poorly designed concurrent patterns. 12.5 The don't communicate by sharing memory. Share memory by communicating mantra. This famous mantra, originating from Tony Hoare's Communicating Sequential Processes (CSB) model, is at the core of Go's concurrency philosophy. It fundamentally guides how you should approach concurrent programming in Go. Explanation: don't communicate by sharing memory. This means avoiding direct access and modification of shared variables or data structures from multiple concurrent goroutines. When you share memory directly, you introduce the complexity of race conditions and the need for explicit locking mechanisms, mutexes, which are prone to errors if not implemented perfectly. Share memory by communicating. Instead of directly letting multiple goroutines write to the same memory location, design your system so that goroutines communicate by sending messages, data, over channels. When a goroutine sends data on a channel, it typically transfers ownership or responsibility for that data to the receiving goroutine. The channel inherently provides the necessary synchronization. When to use channels versus mutexes, channels, are generally preferred for coordination, data transfer, and signaling between goroutines. They implicitly manage synchronization and simplify the mental model of concurrent flow. If data needs to be shared, let one goroutine own and manage the state and communicate with it via channels. Mutexes are suitable for protecting small, localized pieces of shared data, e.g., a field within a struct that are primarily owned by a single goroutine when direct, infrequent, controlled updates are necessary. They are generally used to protect access to state that is not being passed between goroutines, but rather accessed by multiple goroutines concurrently. Benefit: adhering to this mantra dramatically reduces the complexity and bug count associated with concurrent programming. It makes concurrent Go code easier to reason about, safer, and ultimately more robust, allowing you to build highly scalable and efficient applications with confidence. Chapter 13. The journey continues. Congratulations! You've traversed a significant landscape in your journey to mastering Go. From the foundational principles that shape the language to the practical application of design patterns, the pitfalls to avoid, and the essential tools for performance and observability, you've gained a comprehensive understanding of what it means to write idiomatic Go. 13.1 Recap of idiomatic Go principles. Let's briefly recap the core tenets that define the Go way and should guide your development practices. Simplicity and explicitness. Go values clear, straightforward code over complex abstractions. Be explicit about errors, data flow, and dependencies. Avoid over-engineering. Often, the simplest solution is the best. Composition over inheritance. Leverage Go's powerful interface system and struct embedding to build functionality by combining smaller, focused components. This promotes flexibility, reusability, and loose coupling. Concurrency as a core feature. Embrace Go routines and channels to design efficient, scalable, and responsive systems. Always remember the mantra: don't communicate by sharing memory, share memory by communicating. While mutexes have their place, channels are the preferred means of synchronization. Robust error handling. Recognize the importance of Go's explicit error return values. Embrace error wrapping, FMT error with %W, and inspection errors, as to ensure failures are always acknowledged, contextualized, and actionable. Opinionated tooling and testing. Make full use of Go's built-in tools, Go FMT, Go Vet, Go Test, to maintain code quality, consistency, and correctness. Automated testing and benchmarking are not optional. They are integral to building reliable software. Context for control. Consistently use context.context to manage the lifecycle of Go routines, propagate cancellation and timeout signals, and carry request-scoped values, especially in distributed systems. Mastering Go is not about memorizing syntax. It's about internalizing these principles and applying them thoughtfully to solve real-world problems. 13.2 Beyond the Book. Next steps in Go mastery. This book provides a solid foundation, but the journey of mastery is continuous. Here are some pathways for further growth. Deep dive into the standard library. The Go standard library is a masterpiece of well-written, idiomatic Go code. Study packages like net/http, OS, IO, FMT, encoding/JSON, database SQL, text template, crypto, and time. Many of the best practices and patterns we've discussed are exemplified directly within these packages. Understand their interfaces, their error handling, and their design choices. Contribute to open-source Go projects. Reading and contributing to well-established open-source Go projects on platforms like GitHub is an excellent way to learn from experienced Gophers, see real-world applications of patterns, and engage with the community. You'll gain practical experience with larger code bases and different architectural styles. Stay updated with Go releases and new features. Go is actively developed. Keep an eye on the official Go blog and release notes, galling.org/doc/devel/release, for new language features like generics or slog, standard library improvements, and tooling enhancements. Continuous learning is vital in a rapidly evolving tech landscape. Performance tuning in production environments. Apply the profiling, pprof, and observability, logging, metrics, tracing techniques discussed in real-world production systems. Learn from live traffic data, identify bottlenecks, and make data-driven optimizations to your Go applications where it truly matters. There's no substitute for real-world experience. Explore Go microservices, frameworks, and libraries. Investigate popular frameworks and libraries for building microservices like Gin, Echo, Fiber for web services, or gRPC for RPC communication. See how they leverage Go's features and implement many of the patterns we've covered. 13.3 The evolving Go ecosystem. Go continues to grow and mature as a language and an ecosystem. Cloud-native development. Go remains a dominant force in building cloud infrastructure, Docker, Kubernetes, Prometheus, Terraform, and is widely adopted for creating high-performance microservices, robust backend APIs, and efficient command-line tools. Its compiled nature, small binary sizes, and excellent concurrency support make it an ideal choice for containerized and serverless environments. New frontiers. Go is also making inroads into other domains, including WebAssembly. allowing Go code to run in browsers or serverless functions at the edge, data processing, especially with its focus on efficiency, and even some areas of data science. The Go community. One of Go's greatest strengths is its vibrant, welcoming, and pragmatic community of Gophers. Engage with meetups, conferences like GopherCon, online forums like r/Galling on Reddit, the Go Forum, or various Slack channels, and social media. The community is a rich source of learning, collaboration, and support. 13.4 Final thoughts. Crafting elegant and efficient Go applications. The ultimate goal of learning Go is not just to write code that functions, but to craft applications that are idiomatic, maintainable, performant, and reliable. Go provides a powerful and pragmatic set of tools to achieve this. By internalizing its design philosophy, understanding and applying its unique patterns, adhering to best practices, and diligently avoiding common anti-patterns, you empower yourself to build software that stands the test of time. Programming, especially in Go, is as much a craft as it is a science. Approach it with curiosity, a desire for simplicity, and a commitment to continuous improvement. Let the principles of clarity, composition, and concurrency guide you, and you will undoubtedly forge elegant and efficient Go applications that deliver immense value. Your journey into the Go way has just begun. Embrace the learning, enjoy the process, and happy gophering.